Okay. Shift operations. Arithmetic shift operations perform multiplication and division by powers of 2. Works really cool. Very fast, very efficient. They're used extensively in arithmetic routines in all level languages. The operations, the shift operations, affect all of the E-flags bits, and there are 2 types of operations. There are arithmetic shifts and logical shifts. Arithmetic shifts perform signed multiplication and division. Logical, of course, unsigned. So, let's look at arithmetic shift. So, in this case, we're going to perform signed multiplication and division by powers of 2. So, let's say I've got a 4-bit value. Oh, let's say it's an 8-bit value, a byte. And my value is 5. So 0, 0, 0, 0, 0, 1, 0, 1. Okay? And I want to shift left by 1. What I'm going to do is I'm shifting to the left by 1 bit. So 1 bit is going to go away. And in this case, what I'm going to do is I'm shifting to the left. That one goes. Everything else shifts over. And I've got a trailing bit that's opened up. So 0, 0, 0, 0, 1, 0, 1. All trailing bits are going to be cleared. Okay, so my result, this was a 5. When I shift it to the left by 1, it does the equivalent of multiplying it by by 1 power of 2. Since it's a shift to the 1, I am multiplying by 2 to the 1, and my result is 10. Okay, pretty cool. So when shifting left, I'm going to backfill. Let's say we're going to, let me clear all of this, and we'll start over again. This time we want to shift to the right. Shift right by 1. Okay, we'll use the same thing. 5 is our starting point. So, in this case, when I shift to the right by 1, I'm expecting to get something a little bit different. So I'm going to go to the right by 1. So in this case, my rightmost or least significant bit gets shifted out, and that opens up a leading bit. Okay? So here's something different is going to happen. Since this is signed arithmetic, then I'm going to sign extend. So I'm going to take the most significant bit and copy it. Okay? So this does division by 2 to the 1. So 5 divided by 2. What is my remainder? Well, it's going to be 1. What is my quotient? It is 2, and that is exactly what we have left when everything is shifted. Okay? Alright, that's arithmetic shifts. Let me show you logical shifts. These implement unsigned multiplication and division by powers of 2. And I'll show you real quick. Let's do something a little bit larger. Let's say I've got a 16-bit value, BF2C, and I want to do shift left by 4. Okay, in that case, and let's do also a shift right by 4. So we'll draw the beginnings of both of these. Okay, now let's go back to the previous one. and look and see what happens. I want to shift to the left 4 bits. So I'm going to the left. These 4 bits are gone. These bits remain, and I've got 4 bits opened up. Trailing bits are always filled with zeros. Okay, so when I'm done with this one, I'm going to have F to C0 is my result in hex. In this case, I'm going to do a logical shift to the right by 4. So I'm going to the right. These 4 get shifted out to the right. This opens up leading bits. Now, when it was a signed shift to the right, I did sign extension logical shift to the right. I will always 0 fill. Okay? So in this case, my result is going to be 0B F2. Okay? So, the thing to remember is for trailing bits or leading bits, the only case that the bits will not be zeroed out is when I have an arithmetic shift to the right. In that case, it's going to sign extend. So that's the only thing you have to remember. That's the difference in how this behaves. Now, let me talk a little bit. Well, let me talk a little bit about it, but then we're going to look at the instructions. In this last case, we did a logical shift to the right by 4 bits. When I do shifting, the carry flag is going to reflect the last bit shifted out. So in our case, the last bit shifted out was a 1, and that's going to go in the carry flag. Okay? So let me tell you a little bit more about how to use them, what to use them for, and all of that. Arithmetic shift operations, I've actually got 3 different sets. Arithmetic shifts to the left here, and then arithmetic shifts to the right. The destination, fine, but how I handle the source. It's either going to be a 1 or an 8-bit immediate value, or if I'm going to be doing this inside a loop and I want to make it a little more efficient, I can put that 8-bit immediate value in CL. Okay, same thing with the arithmetic shift to the right. In this case, let me show you something. I've got 2 different types of shifts. I've got a single bit shift, and I've got multi-bit shifts. These are going to behave a little bit differently depending on what we're doing. So let's do the logical. These were arithmetic shifts. Let's do logical, then let's talk about the rules. The rules are the same except for how we fill in leading bits, and we've already talked about that. We'll go over it again. Don't worry about it. So I've got the same layout for the logical shift operations. I've got single bit and multi-bit shifts. Let's talk about the rules, okay? The destination can be byte word or double word. In register or memory, no immediate value, as usual. Okay? The immediate 8 source for either one of these can be, since it's an immediate 8-bit value, could be 0 to 255, but how many bits do I have to shift in a 32-bit destination? I only have 32. So a 255-bit shift in a 32-bit register doesn't make sense. So for both immediate 8 and CL, since those are both 8-bit immediate values, or 8-bit values, one is an immediate, one stored in a register, they'll be reduced by modulo 32 before the shift occurs. Okay? All shifts to the left will backfill with zeros. Logical shifts to the right will zero fill leading blanks. Arithmetic shifts to the right will sign extend leading bits. Okay? All right. And last thing is, remember, you cannot have over 32 meaningful shift operations to an operand when the operand is no longer than a double word. Okay? All right. Now, let's talk about E-flags. What happens with E-flags? Well, we talked a little bit about the carry flag. Okay? So, carry flag is the last bit shifted out. Sign flag, zero flag, and parity flag. They're assigned according to the final value in the destination. Okay, so if the destination is positive, sign flag will be cleared. If the final destination is zero, the zero flag will be set. The final destination has an even number of ones in it in the binary, then the parity flag will be set to make odd parity. Now, this one is tricksy. So let's do it a couple of ways. It is undefined for multi-bit shifts. That means put a question mark if I ask. Okay? For single-bit shifts, it will be 0 if the sign of the result is the same as the sign of the original, cleared otherwise if no sign change, 1 otherwise. Okay, so for single-bit shifts, the overflow flag will tell me if there's a sign change between the original destination and the manipulated destination. But it is undefined for multi-bit shifts. Okay? All right, so let's do some examples. Make this a little bit clearer or muddy the waters. Hopefully not that. All right, this says we're doing an arithmetic shift to the left on CX, 1 bit. Okay, so here we'll assume CX has this value before the shift. This is what it looks like in binary. I'm going to the left by 1. Okay, so after the shift, the 1 is out, opening up a trailing bit. All trailing bits are 0 filled. So CX after is going to be 0, 1, 0, 1. 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0. Okay? Or A, 3, A, A, E. When we're done. Okay? Now, let's look at sign flag, carry flag, zero flag, overflow flag. Sign flag. What is the sign? Oh, that's not A. Let's mark that out and say that is 5, 3, AE. Oh, that's much better. Okay, so this is a positive value, so sign flag will be cleared. Okay, carry flag, the last bit carried out was the only bit carried out, and it was a 1 right here. Zero flag, it is not 0, my final result, so I'm going to clear the 0 flag. And finally, this is a single bit shift. So overflow reflects if there's a sign change. Well, before it was negative, and now it is positive. So overflow flag will be set to indicate a sign change. Okay? All right, let's do another one. This time we're doing an arithmetic shift to the right. We've got the same starting value by 1 bit, so we're going to the right. This gets shifted out. It's an arithmetic shift to the right, so I'm going to sign extend my leading bit. And in this case, that's my final value. Let's just kind of look at this and say, in hex, this is going to be D for E B. Okay, so sign flag, zero flag, carry flag, overflow flag. Sign flag. My result is negative. Sign flag will be set. It's not 0. Zero flag will be cleared. Carry flag, last bit shifted out, was a 1. And it is a single bit shift, therefore the overflow flag will indicate if there's a sign change. That was negative to begin with. It is still negative, so overflow flag will be 0. So in this case, only the carry flag and sign flag will be set in this case. All right, now let's do a multi-bit shift just to see what the difference is. Okay, this is going to be a logical shift to the left this is a logical shift to the right by 4 bits of dx. So here I've got, again, my same starting values. This is a logical shift right by 4. So these 4 bits go out. Carry flag is 0 because that's the last bit shifted out. Sign flag, 0 flag, overflow flag. And it is an arithmetic shift, so my leading bits will be zeros. So my value when I'm done is going to be 0, A, 9, 7. Okay? So, carry flag is 0, last bit shifted out. Sign flag, this is positive. Okay? 0 flag, it's not 0. And overflow flag, well, you say, oh, well, it was negative, now it's positive, but it's a multi-bit shift. So overflow flag is actually going to be undefined. And let me just tell you why it's undefined. You can predict it, but what it's going to do is it's going to set or clear based on every bit getting shifted out and what the result is after every bit. Okay, so you can't tell because after the third shift, if it were to work, it would reflect only the change in sign between the third and fourth shifts, not between the first and fourth. Okay, so that's why that one is not defined. All right, one more. Let's use CL as our source just to get a little practice. This one will be a logical shift to the left of AX by CL. CL is 4, so logical shift to the left. Trailing bits are always 0 filled, so my answer afterwards is 9D70. Carry flag, 0 flag. Sign flag, overflow flag. Well, this is multi-bit, so we know overflow is going to be undefined. Sign flag, this is a negative value, so it'll be set. It is non-zero, so 0 flag will be cleared. And the last bit shifted out was a 0. So in this case, my only bit that is set is going to be the sign flag. Okay? All right. So in class, we'll do a series of examples. And I think I'll pause here because we'll pick up with rotates next.